Okay, here I'm testing my iPad to see if I can broadcast from it. So let's suppose we want to analyze a function, f of x equals x squared. So quick graph of that sucker. And let's take a look at it on the interval from 0 to 2. And so we know we're going to have a point at 0, 0, and 1, 1, and 2, 4. And we know it's shallow near the base, and then increases from there. So what we want to do is estimate the area between 0 and 2. So that's this region right here. So we're going to build up some rectangles into what's called a Riemann sum. So to do that, we have to decide how many intervals we want to make. Now, in class the other day, we played around with 4 and 10. And so here I'm just going to say I want n subintervals. And now I have to figure out what the width is going to be. Now, you can have variable widths to the intervals, but that's kind of tricky. I find the easiest thing to do for a lot of function is to go with fixed width right-hand endpoints. That's what we're going to do here. So keep in mind that the width of my area of interest is the right-hand value 2 minus the left-hand 0, so I have a width of 2. So I want to make little widths, my delta x's, and they're going to be the width of the whole interval divided by the number of subintervals that I want. So in general, each little x rectangle will be 2 over n. Now here, to generate x values to go with this, you always go with whatever the left hand, if you're doing right-hand sums, which is what we're doing, you take the left-hand boundary, and then you add multiples of the width repeatedly. Cleaning that up, I get each x value for the right-hand endpoint, again, emphasize right-hand endpoint, is going to be 2i over n. So I is my counter. Okay? And I is going to go from 1 to n. So if I were to expand this right here from 0 to 2, then I'm going to jump over for the first one. That will be 2 over n. Oops, this was n. And then the next one will be 2 of those, so that would be 4 over n. And then the next one is going to be 6 over n, and so on down the road, all the way till I get to the last one here, right-hand endpoint. That last one is going to be 2 times n over n, because each time I plug in a new value for I, so that ends me at 2 there. Now here it's nice because we're starting at 0. If we started at 1, we'll try that later. It gets a little more tricky, but that's all right. So then each rectangle, oops, that's my highlighter. And let's switch colors. Each rectangle, let's call that delta area, a little chunk of area, is going to have a width of 2 over n and a height where I plug the given x value into my function. Way up there, right there. All right, so that means I'm going to square each of these guys here. So I'm going to have a 2i over n squared. So each rectangle's area is going to look like that. So then I need to add those suckers up. So now I'm going to have a summation as I goes from 1 to n. and each rectangle has a base of 2 over n and a height of 2I over n squared. Cleaning that up a little bit, I get a sum, excuse that teenage noise in the background, quiet down shortly. So I'm going to have a 2 over n, and then I'm going to square that thing inside, so that's going to be a 4I squared over n squared. Now, the summation has a variable, an index of I, so the i's are stuck in here, but everything else is fixed. So for example, n could be 10, right? So it's a fixed number, whatever n happens to be at that point in time. So cleaning this up, I can pull out the 2, I can pull out the 4, I can pull out the n and the n squared. So that's going to leave me on the outside a constant of 8 over n cubed, and on the inside I am stuck adding up the I squareds. And the other day in class we looked at a formula for those I squareds. So the 8 over n cubed is just hanging out. And when I add up the squares of the counting numbers, I end up with n times n plus 1 times 2n plus 1 all over 6. Putting that all together. Now, there's really no point in multiplying out the top. That's kind of a waste of time. And so then we can just say, let's see, the 8 over 6 cleans up a wee bit to what, 4 thirds, and then I have n, oops, that was an n cubed over here, wasn't it? There we go. And then I'm going to have n times n plus 1 times 2n plus 1, all over n cubed. So what this gives me is a general formula. This is called a Riemann sum with right-hand endpoints, so that if you tell me how many rectangles you want to use, this formula will tell you what the area of all those rectangles added up are. Now we can take this a step farther. What we can do is we can take a look at the limit as n gets bigger. So we get more and more rectangles, they get thinner and thinner and thinner, right, of our original Riemann sum. So as I goes from 1 to n of 2 over n times the 2I over n all squared. We know that that sum is equal to the fraction above, so that means my limit as n increases is 4 thirds times n times n plus 1 times 2n plus 1 all over n cubed. Now notice here, let's get my highlighter out, that I'm going to have an n times 2n in the top. So that's going to ultimately lead to a polynomial of degree 3 with a leading coefficient of 2n cubed. And if I take the limit as n gets big, if the degree of the numerator is the same as the degree of the denominator, then the limit is the ratio of their coefficients. So that means in the limit here, I'm going to get, back to my pen, the 4 thirds is just chilling out front, and then the limit of that fraction of n is going to be 2 over 1. And so finally, I get an area here of 8 thirds. And so I'm just going to check with a computer algebra system to see what it thinks about the area inside. So the claim is here that for any number of rectangles with right-hand sums for the area under x squared between 0 and 2, that this right here is the area of the rectangles. And if we let n get bigger and bigger, and that makes the width of each rectangle get smaller and smaller and smaller towards 0, the limit, the most those rectangles can possibly equal is 8 thirds. So GeoGebra, I got the desktop version here. It's a lot of date, but it should still work. So I want to graph x squared, and then I'm going to ask GeoGebra to give me the integral. We'll talk more about integrals shortly, of f starting at 2, no, starting at 0, excuse me, and ending at 2. And it says that's about 2.67. It's below that a little bit so you can see better. Font size 24. That's a little bit better. Okay. And if you take 8/3, that would be 2 2/3. So GeoGebra, my computer algebra system here, agrees. Wolfram alpha is another good one. Let's take a quick check with Wolfram alpha. Where the heck is Wolfram alpha? Over here somewhere. Another nice tool. Wolfram alpha. I mentioned it in class, but I haven't used it yet. And so you can type mathematical expressions in here. If you type it right, it will get your meaning. So I want to find the integral. So tell you I recognize that. And then it'll tell me more about integral here. In parentheses, I want the integral of x raised to the second power from 0 to 2, and hopefully we'll interpret that. I'm hoping. And it says, yeah. And an integral is a way of finding the area under a curve, which is what we're aiming at here. And again, we took the limit of a Riemann sum. So I'm going to come back with another recording where we'll do a few more examples of this to try and get used to it. And it looks like my iPad is going to work just fine.